Lesson 1.3, Solving equations with variables on both sides. So far we're pretty deep into solving equations. Now this is a very specific lesson where we're going to get equations where the variable appears on both sides of the equation, and because of that it's going to create certain problems for us which we're going to learn how to deal with. So your job is to understand how to solve these equations where the variable appears on both sides of the equation. So one of the things that we're going to revisit is the idea of viewing equations as a balanced scale. When it comes to equations with variables on both sides, this is once again a really helpful visual of how we might go about simplifying the problem. So here's my equation. I specifically chose this one because it has 2x on one side, but then on the other side it's got 1x. And so this is something new for us. So first off, let's do like we've done in our previous notes, and let's simulate 2x plus 4. And on the other side, x plus 8. And so like before, the balance scale will first tip one way, but now the other because it's now balanced out. And the question that we want to ask ourselves is, well, how could I simplify this picture? Well, one thing we talked about was that before we understood that, well, you know what, I could take away 4 tiles from each side because that would keep things balanced, yet simplify the picture. So in fact, I'm going to do that right now. Let's continue. I am going to subtract 4 tiles from both sides. And as you can see, our balance scale doesn't tilt, it remains balanced. Now what we want to think about is, are there any other ways that we might simplify this picture before doing any other manipulations? So one thing you might notice here is that, well, just like we had these blocks of weights, we also have these mystery blocks of x. I've got 2 of these x's on one side and 1 on the other. And so just like with the other problem, what I could do is I could subtract 1x from both sides, and just like with the weights, take those away, and it simplifies the picture even further. And in fact, on this problem, we get our answer. 1 block equals 4 tiles. And so this is how we deal with variables on both sides. We treat them just like the weights, and by either adding or subtracting them, we can get rid of them on one side. Here's another example with our balance scale, and then we'll move on to some other pencil and paper examples. 4x plus 5 equals 2x plus 3. So once again, we simulate 4x, 1, 2, 3, 4, 5, and then over here, 2x plus 3. So in fact, this time I think I'll start with the x's first. What I see here is I've got 4 of these mystery blocks on this side, 2 of the mystery blocks on this side, and so what I could do is I could take a maximum number of, subtract 2 blocks of x, or 2x from both sides, and right away my picture gets a lot cleaner. I go from 4x plus 5 equals 2x plus 3, an equation that's somewhat unfamiliar to us right now. And now it looks a lot like the work from the previous day. Now we've just got 2x's plus 5 equals 3. And now we can use our steps, our roadmap technique, to take it the rest of the way. Alright, so let's take a look at some examples. Alright, so these examples were specifically chosen because they all have something in common, which is that they both have variables on both sides of the equal sign. And this is something we haven't seen before. And so just like with the balance scales you saw on the previous slides, what we're going to try to do here is we're going to try to incorporate this into our process so far. And so what it looks like is something like this. Step 1 has not changed. That before you ever get into the solving of the equations, that the first thing we want to do is to simplify things, to make it a little bit cleaner and easier to work with. So if you see parentheses where some distributive property could be done, we want to clean that up. If there's any like terms that we can combine, either on the left or the right, we do that first. Alright, then here's the part we're adding in today. Is that what's confusing about this equation compared to all the others we've done so far is the fact that we've got variables on both sides of the equation. And so our job in step 2 is to separate the variables to one side of the equation or the other. And it doesn't matter which one. You just want to do whichever is easier. And then finally step 3, which is something we've been working on for the past 3-4 days, which is to actually solve by doing opposites, and then to incorporate this idea of the roadmap where we do things in the opposite order. All right, so let's take a look. Let's apply all those steps. So step 1 is simplify. Well, I don't see any parentheses to do distributive property. And these like terms are on opposite sides of the equation. I can't just move them. So step 1, there's nothing to be done. All right, so now step 2 is separate the variables to one side. All right, so I think what I'm going to do here is, the way I'm going to separate those out is I'm going to get rid of this 2x. That way I've got variables on one side and my numbers on the other. Okay, now remember, you're not trying to just get rid of the 2 here. We're trying to get rid of the entire 2x. So they've added 2x. We're going to do its opposite. Subtract 2x, subtract 2x. Okay, these will cancel out. And we accomplished what I wanted in step 2, which is now I've got all the variables separated to one side. I've got negative 5x on the left side equals 19 on the right side. All right, now in this case, I could do the roadmap, but really there's only one step. Here they've got x times by a negative 5, so we're going to do its opposite, which is to divide by negative 5. Divide by negative 5. These cancel, leaves me with x. And this isn't reducible, so I'm just going to leave this as 19/5. Okay, but the key element here is what we did here. This is the new step. This idea that anytime you see variables on both sides of the equation, you need to get rid of one of them to make it look more like the work we've been doing. Now, the question that usually comes up here is, well, why did I pick the 2x? Okay, and this is something you'll start to see as you get better at this. Let's say I take the same problem. Watch what happens if I had done the other thing, which was to get rid of this negative or minus 3x. So that work would have looked something like this. I would have checked to see if I could simplify it, which I can't. I then would have added 3x to both sides. These cancel out. Now in this case, I just can't leave the left side blank, so I'm going to leave a filler 0 in. 5x plus 19. Okay, so now my roadmap would look something like this. I've got x, which has been multiplied by 5, and added 19. So I'm going to pull my U-turn and do the reverse moves in the reverse order, which is to subtract 19 from both sides. And then divide by 5. And I get x equals negative 19/5, just like before. But if you take a look at the work, notice how this one is a little bit longer. I had to do one step more here than I did here. And so hopefully you'll start to get an eye for this, that, if you do it this way, no big deal, but you have made extra work for yourself. And the way I came to the decision of doing it this way is, well, I realized that at some point in the process of solving an equation, I want to not only get my variables to one side of the equation, like step 2 says, but I eventually want all the numbers on the other side. So when I was looking at this, I figured, well, you know what? My numbers are already on the right. So a smart move would be to get all my variables over to the left. So that's what made me pick this 2x to get rid of, because it saved me a step in the process. Here, I didn't use that logic, and it just took an extra step. Still got the same answer, but if you can start to see the reasoning behind that, it'll save you some time and effort. All right, let's do a few more examples. All right, let's take a look at this one. So, step 1, simplify if you can. Now in this case, I do see something we can simplify. We can get rid of these parentheses and clean things up by doing distributive property. So 6 times 4 is 24. Minus sign drops down. 6 times z is 6z equals 2z. All right, step 2, we don't like the variables on both sides of the equation. It's confusing, so we need to get rid of one of them. Now, once again, if you use that logic that I was showing you, notice the 24. The 24 is fine where it's at, which means my numbers are on the left side of the equation, which means it would be handy if I could get all the variables to the right side. So of all the things that are out of place, it's this one. So what I'm going to do is the opposite. Instead of subtracting 6z, I'm going to add 6z. Those will disappear. I'll get 24 equals 8z. And notice how I'm just down to one step. 8 times z. The opposite is to divide. And I get z equals 3. Okay, I won't do it a second time, but if I had gone the other way and subtracted 2z from both sides on this step, again, I would have ended up with one extra step later on, and just makes it faster. Okay. All right. Now, how about this one? Nothing to simplify, so now I need to separate the variables to one side. Okay, but notice here, I have numbers on both sides too, so it really doesn't matter which one I get rid of. The only thing I might suggest is maybe for a lot of people, you might want to get rid of this one. And the reasoning there to subtract this particular set of y's away is that when I get to this step here, 4.5 minus 2.5, I get 2y. And the reasoning behind that is because if I had done minus 4.5 minus 4.5y, when I subtracted, I would have ended up with negative 2y over here. Not a big deal. We know how to do our negatives, but you know, one less negative in the problem is just one less area to make a mistake on. So I chose to do it that way so that I get positive 2y. Again, it's one of those things that comes with experience, and I think the more you do these, you'll start to see it. All right, now we've got a couple things to do here, so let's do our roadmap. Looks like they've got y, and the first thing they did to it was to multiply by 2 and then subtract 1. So I'm going to pull my U-turn and do the reverse moves in the reverse order. So I'm going to add 1 to both sides. That'll make this 7 equals 2y. They multiplied by 2, so I'm going to divide by 2. And so y equals 3.5 or 3.5. Okay. All right. Now, this last set I picked out because these are some special cases we need to be aware of. And what I mean by special cases is, as we do these problems, something weird is going to kind of happen here. So I've got 2 to just kind of explain this. All right, so 2x plus 4 equals 2x minus 3. And so first thing would be to simplify, but I don't see any like terms. I don't see any parentheses, so I move to step 2. I don't like variables on both sides. So let's just say, for example, I focused in on this one. I'm going to get rid of this 2x by subtracting the entire thing away. What I do to one side, I do it to the other side of the equal sign. Now here's where the weird thing happens. Minus 3 gets recopied, equal sign gets recopied, the positive 4 gets recopied, but then over here, 2x minus 2x, that's 0, and this also cancels out. And so I run into this problem that the variable that I was solving for disappeared. So x disappeared. Now, not only did my variable disappear, that what was left over doesn't even make sense. And so it's because of those two things that we run into this special case. That one, my variable that I was trying to solve for disappeared, and the remaining equation, 4 equals negative 3, isn't even mathematically valid. What this means is that this problem was bogus to begin with, that somebody created an equation that was unsolvable. So what we would write here is no solution. This problem had no solution to begin with, and so these are the two criteria that tell us that in the process of your work, the variable that you were solving for disappears, and then whatever's left over doesn't make any kind of sense at all. And this means there was no solution to begin with, and that's what you write for your answer. Now, which is a little bit different from this one. And just ignore my extra parentheses here. This shouldn't be here. All right, so in this problem, let's go through our steps again. Let's just assume it's a normal problem. So first thing is we clean things up. I see some distributive property here we could do. And I'm going to get a half times 6t, that's 3t, minus a half times 4 is 2. And let's copy the right-hand side down. Okay, and I think some people will start to see it already, but let's keep going. So the next thing here is I don't like variables on both sides. So let's assume I'm getting rid of this one, 3t. So I subtract away 3t, subtract away 3t. And the same thing that happened up here happens here. I purposely got rid of this one, but then in the process of getting rid of that 3t, this set disappeared also. And I get this. So once again, the variable that I was solving for disappeared. Okay, but notice the difference here. That this time the leftovers make sense. Okay, even though it's not the answer we were looking for, that t disappeared, and negative 2 does equal negative 2. All right, and so what this means is not no solution. In fact, it means almost the opposite, that I could have picked t to be anything I wanted it to be. That there's infinitely many solutions that I could have chosen here. And in fact, I'm going to show this to you. So let's say, just off the top of my head, I pick 5. Well, 6 times 5 is 30. 30 minus 4 is 26. Half of 26 is 13. If I put 5 in over here, 3 times 5 is 15. 15 minus 2 is 13. 13 equals 13. But then let's say I pick a different number. Let's say I pick 2. Well, 6 times 2 is 12. 12 minus 4 is 8. Half of 8 is 4. If I do that over here, 3 times 2 is 6. 6 minus 2 is 4. 4 equals 4. And so basically what happened here was that even though it didn't look like it initially, the left side of the equation and the right side of the equation were identical. And so it didn't matter what t was. T could be anything you want it to be. It could be 0, it could be a million, it could be negative 2.8. No matter what, it's going to work because the left side and the right side, the math is exactly the same. Okay, and so once again is that you do your work up to this point, and you're looking for, again, two things. That the variable that you were solving for disappeared, just like it did up here. But what's different about this scenario is that what's left over makes mathematical sense. Negative 2 did equal negative 2, and so that's how I know it's infinitely many solutions. I can pick t to be whatever I want it to be. Okay, so that's a little bit on solving equations with variables on both sides.